Alright, in this video I will talk about the different FSMs that I created in Logisim to simulate the elevator control system. So this is the first draft of my FSM. You'll notice that the outputs over here are different from the elevator control outputs. This is because I wasn't familiar with the up-down system. But these are essentially function in the same way. So it starts off very standard. There are 16 buttons, each representing a data line that represents a floor. Above that we have the clock that feeds to all the registers, as well as a reset button. So standard procedure, the buttons all feed into 4-bit registers, and then from the output of those is fed into priority encoders. The priority encoders will then output their will output the lower dimensional signal into these set of gates, which will then, using the multiplexer, feed it into the last register. So there's a couple things about here that you don't actually have to implement when you're building the circuit. One of these is this pin that I have here. Essentially, these priority encoders in Logisim have a problem whereby if, for example, if I'm using the bottom 8 here, what'll happen is in the top priority encoder, the output, instead of being zeros, will be x's. I could not figure out how to fix that. There is even a setting where you say you can change this disabled output to 0, but because input is enabled, it still outputs a floating. So the way I counteracted that is I said that if there is no input being passed into the priority encoder of the top, then just select 0, 0, 0 as your output. This also works the same way for the bottom. So basically, if one of the encoders is not in use because the button being pressed is associated with a different one, just output a 0 for that one. Next, these gates look different from just the 4 AND gates that we'll actually use in the circuit. Reason for this is the signals in Logisim are active high, whereas in the actual circuit components they're active low. So just have to use a slightly different logic to get the same thing. And then also, in this draft I had not included the latched encoder. It's interesting, in Logisim you don't actually have to include a latched encoder. For whatever reason, it seems to remember what you put. I think that's probably just with how I built the select input. So then the next thing that happens is very standard. You compare the encoded desired floor with the current floor. And for the purposes of this, I decided to just set the current floor to start on floor 0. It doesn't matter where it starts; it could start anywhere. But for simplicity's sake, I started it on floor 0. So these two signals are compared, and based on the output of the comparator here, we will either tell the system to go up, go down, or stay idle. So right now, both of the desired floor and the current floor are ground, so the floors are equal, so nothing needs to happen to the up-down counter. What I've implemented over here is essentially a full adder and a full subtractor. This is not actually present in the circuitry that you physically build, but the purpose of that is these adders is to simulate moving up and down. So let me give you an example of what I mean. And also I need to set these to 1 so that you'll either add or subtract 1 from the input. Okay, so let's take floor 4. I'll propagate that down using the clock up here, and then we'll see on the desired floor we want to go to floor 4. The current floor is set to ground, so we need to go up, as this system indicates. So now what we can see is that it is the full adder that is going to be affected here, and so the output from the full adder will be passed through this multiplexer, which will then get re-recorded in this register. So we can see if we use the clock once, then it ticks up from ground to 1, and then it goes back. And so it can keep going as such, and then once they reach floor 4, we're idle. Now there are a couple of requirements that we're required to make for the purpose of the project. One is that if you select a floor, and if we select a floor, so 8 is selected and we start moving, we should be able to select a new floor, we'll say 2 in this case, and interrupt the current path. And so this circuit absolutely can do that. One other requirement is if we select ground, then we're supposed to go to ground and until we reach ground and not stop until then. This circuit cannot do that, and that's one of the things that I addressed in the next draft I built, which is this one here. So this draft is a lot better. It's slightly more compressed. It still has some of the annoying features, like you have to include the 0 pin, but it also includes the up-down that is used on the actual elevator controller. And it also incorporates the if you select ground, it goes all the way to ground without stopping. It incorporates that. So the way that this works is still very similar. For all pins from 0 to 15, you can select a pin, update a register, move through a priority encoder, through some logic, and then get a final output here in the multiplexer. In the final register. What's different that I've added here is, one, I've included inputs for the floors, just with pins. You can set these to whatever you want. This simulates more closely what the actual elevator will give me. And additionally, I've added some logic here that will lock the elevator in a path to ground if ground is selected. Okay. So first I can show that it works normally as intended. So let's say we're starting on floor 2. Oh, that's another thing you can do. You can simulate new starting conditions with this setup. So if we're on floor 2 and I select floor 12, then after... sorry. This has to be enabled. Okay, sorry. So I select floor 12. So what we can see is that we're currently on 2 and we want to go to 12. These representations are in binary. I got rid of the decoder for this simulation. And so we can see that just using the comparator and 2 logic gates, we're telling the circuit to go up. And then for the purpose of this, I've just created a black box here, and so we'll assume that the circuit knows to go up. We can say, okay, the circuit keeps going up. We get 1 floor up, it still needs to go up. We can speed this up a little bit. Let's say we get here, still need to go up, keep going up. And let's say we finally reach, let's say we get 1 before here. And then we finally get to the floor 12 that we want. And we have both lights active. So both lights are active, meaning the elevator will now be idle. It works the same way. Say we're now on floor 12 and we want to go down. We can see that now that we have this new floor, we have floor 6 put into the register, we're now going to start going down. And once we reach floor 6, we're idle. So the way that I've implemented the determined path down to the ground floor if you press the ground button is I've used a set of latched multiplexers in order to lock the floor 000 as the desired floor if you press ground. So let's just reset everything real quick. So let's say we're currently on floor 6. So if I press ground, what we can see is that the multiplexer here is activated, and no, actually I probably don't even need this multiplexer. This could just go straight into, yeah, whatever. Okay, so the multiplexer is activated, and then this multiplexer, it will then feed into the next register. Now, the register here is being reset because the system thinks that both floors are equal. However, if I update it so that we now think we're on floor 6, we can see that the floors are no longer equal, and so the register is no longer being reset. So if I go through and update the register now, it is being set to 1. And now this is activating this multiplexer, which is selecting 000 over whatever other input that we put here. So I can still go through and I can put 9. Here, let me put a pin here so we can visualize what's coming out of this. And then we'll just bump this up to 4. Okay, so I can put whatever I want in here. We can put 12, 14, 15, whatever, or 16, or 15. But whatever we put in here, there is still always going to be a 0 in the desired floor because of how this multiplexer is set up. And we keep going down up until we hit floor 0. And once this has been updated, then the equals part of the comparator comes out. It deactivates this register. The output then goes to 0 here, and then once this is set at 0, then any other input from the normal ones can be input. Oh, I remember why I use this multiplexer here. The reason for using this multiplexer here is once you have activated this, if you let go of the ground button, then this select goes to 0, which means that you'll be selecting the top channel instead of the bottom channel. And you don't want the top channel to go to 0 once you stop pressing the ground button, so we latch the output of the register using this multiplexer. So this FSM completely encapsulates all of the requirements for the FSM elevator, and so yeah, that's that.
Alright, so this is a preliminary demonstration of the encoding part of the elevator. So what I'm going to demonstrate in this video is that this circuit here can encode the input from the buttons into 4-bit binary. So I'll start by talking through how this circuit works. The inputs are these 16 buttons here, each one representing a different floor on the elevator. So what's happening is the inputs from each of these buttons are high unless you press the button, in which case they turn low. And so these data are then stored in these 4 registers here. And then the output from these registers are sent into 2 priority encoders. The purpose of the encoders is they can represent these 8 data lines at a time as 3 outputs. And so when you combine 2 of them and cascade them according to the schematic we have, you can create a 4-bit representation of 16 lines of data. Then these 4 bits of data are then using this multiplexer here. They will be stored and held in this register. The purpose of the multiplexer is when you press a button and you input a floor into the circuit, you want the register to hold the value of that floor until some condition is reached. And so the idea with the multiplexer is that it'll continue to hold the value of the floor, and it won't release it until a new... Now we can go ahead and test out this circuit. So I'll press the button, turn on the power. We can see that the clock is flashing. And when I press 0, we can see that there is the value of this floor is stored as ground. Now if I press 1, we'll get 1 latched in the circuit. I don't know, we'll press 6, we can see 6. I don't know, 15 works, 14. Every value of the floor can be stored and represented in binary. So I've gone ahead and implemented the comparator, and when I set both equal to 0, you see that we get both lights are red, and when I set the floor input to 15, I press 15 here, just the up button is red. So I have, for sake of testing, I have grounded all the inputs for the elevator. So this means that the circuit thinks that the elevator is on floor 0.